We'll wait for about 5 minutes to let everyone join and then we'll start the session. Hello everyone. Welcome to the fourth TA session for Drug Delivery Principles and Engineering. I hope everybody can hear my voice. Can someone confirm?
Yes, ma'am.
Okay. And can you see my screen as well?
Yes, ma'am.
Okay. Okay. So we'll start the session. Before we start, this entire session is being recorded, and the slide all as well as the session will be shared with you all. So these were the topics that were covered in the previous week. It was basically nanoparticles and microparticles, what they are, how to characterize them, and how to prepare the nanoparticles and microparticles, all those things, including liposomes. So I have some previous year questions regarding on this topic, and we'll solve them one by one. Here is the first question. What is proton sponge effect? You have to select two correct options here. Options are: the particles carry secondary or tertiary amines, which helps in escaping endosomal and lysosomal vesicles inside the cells, or it is a phenomena which leads to osmotic swelling and bursting of vesicles, or particles act as sponges for electrons. The phenomena where particles carrying positively charged moieties neutralize free radical moieties in an extracellular environment. The phenomenon of gaining positive charge during endosomal transport. A sponge soaks up all protons in the vicinity, or the phenomena of gaining negative charge during endosomal transport. Which of these options do you think is correct for proton sponge effect? If you know the answer, please unmute and let me know what you think the correct answer is. Can anyone answer? 1 and 5. Okay. If possible, please try to unmute and speak the answers. Till now, only one person has answered option 1 and 5. What about others? Which two options do you think are correct here regarding proton sponge effect? Anyone?
I'm 1 and 5.
1 and 5. Okay. Okay, let's look at the answer. So the correct answer would be 1. Particles carry secondary or tertiary means which helps in escaping endosomal and lysosomal vesicles inside the cells. The second is phenomenon which leads to osmotic swelling and bursting of vesicles. So the fifth option talks about gaining positive charge during endosomal transport. This is not related to endosomal transport. Basically, it's escaping out of that, and it already has positive charge due to the amines. So mostly the particles that are engulfed by the cells end up in the endosomes or lysosomal vesicles, and most of them get degraded if they are in the lysosomal compartments. So to escape from that lysosomal compartment into the cytosol, they use something called as proton sponge effect, where you can design your particles such that it carries secondary and tertiary amines, and that will buffer the pH of the endosomes and will result in proton influx through the endosomal proton pumps, and that will be followed by chloride ion transport, which leads to osmotic swelling and bursting of those vesicles, and ultimately your particles will be out of those compartments into the cytoplasm. So polyethylene imine is a widely used polymer for this phenomenon, and the conjugation of peptides that can create pores in endosomal membranes, all those things have been also proposed, but mostly it's the uh, secondary and tertiary amines that are mostly used for this proton sponge effect. Okay, here is the next question. Which one is not correct about dendrimers? And the options are, they are like polymers branching out from a central core and subdividing into hierarchical branching. They are generally not more than 100 nanometer in size. They are very dense surface surrounding a relatively hollow core. They have very high molecular weight. The entire structure can be divided into generation of shells. Branch density increases with each generation. The size of dendrimer depends on the number of generations, or they are generally more than 100 nanometer in size. Here there is only one option that is correct, and which of these options you think is not correct about dendrimers?
Second one.
They are generally not more than 100 nanometer in size. Okay. Anyone else would like to answer? I'll come to your question, Bhavadharini. First, let's finish this one. Which one is not correct about dendrimers?
The size of dendrimer depends on the number of generations.
Okay. Anyone else has any other answer? So till now we have option 2 and option 5, option 7. Anybody else? Okay, the correct answer would be they are generally more than 100 nanometer in size. So dendrimers are usually very small in size. So they are generally not more than 100 nanometer size is in fact correct. And then the size of dendrimer depends on the number of generations. That is also correct. So dendrimers are like these branch structures and tree-like polymers. So they are not more than 15 nanometer in size, and initially there will be a layer, and then there is second set of branches and third set of branches. So based on the number of branches coming out, each branch is like each generation, and uh, yeah, each shell is called a generation, and the branch density increases with each generation. So the size of the dendrimer also depends on the number of generations. For example, a 2 generation will have a smaller size as compared to a 4 generation dendrimer. So the only option that is not correct here is they are generally more than 100 nanometer in size. Ranking. So here is the third question. Ranking the order of clearance of charged molecules. Pick the right one. Uh, just uh, yeah, someone has asked a question that endosomes are acidic in nature, and when these particles containing amines enter the endosome, they gain H plus ions. Yes, they'll take up from there and gain H plus, which is why that is how it is going to buffer this system. It will result in more proton influx to balance whatever ions is lost from the compartment. Okay, so moving on to the third question. Here you have to rank the order of clearance of charged molecules to pick the right one. Assume all particles are of same size and below 6 nanometer. So these are the options. Negatively charged nanoparticles are cleared faster than neutral ones, followed by positively charged nanoparticles, owing mainly to interactions with the glomerular placement membrane. GBM. Neutral nanoparticles are cleared faster than positive charged ones, followed by negatively charged nanoparticles, owing mainly to interactions with the GBM. Or positively charged nanoparticles are cleared faster than negatively charged ones, followed by neutral, owing to interactions with the GBM. Positively charged nanoparticles are cleared faster than neutral ones, followed by negatively charged particles. Negatively charged nanoparticles are cleared faster than positively charged ones, followed by neutral nanoparticles. And neutral charged particles are cleared faster than negatively charged ones, or none of the particles get cleared away, or all the particles get cleared at the same rate?
Fourth one.
Option 5.
Fourth and five. Sorry?
Yeah, fifth. Fifth.
Fifth one. Negatively charged nanoparticles are cleared faster than positively charged ones, and then followed by neutral. Okay. Okay. What about others?
Fourth one.
Fourth one. Okay. Anybody else has any other options as their answer? Anyone else? Okay, so the correct answer would be positively charged nanoparticles are cleared faster than neutral ones, followed by negatively charged nanoparticles, owing mainly to interactions with the basement membrane. Glomerular basement membrane. Okay, so we have the basement membrane here, and then these are endothelial cells. So these endothelial cells has glycocalyx, which forms the charge layer 1, and then we have the basement membrane, which is charge layer 2, and the podocyte glycocalyx. These also have a glycocalyx coating, which is the third layer of charge. So if your positively charged particles are there, they'll be attracted fast because of these negative charge, as compared to your neutral or negative ones. So negative one would be the most repelled one, which is why we have the first positively charged nanoparticles are cleared, and then neutral ones, and then at last you'll have negatively charged nanoparticles cleared, because all of these will have, most of these will have negatively charged. There are three layers of negative charge already present. Now, here we have the fourth question. Which one of the following is correct with regard to elasticity of particles? Stiffer particles with high modulus of elasticity can circulate for longer duration since they cannot be degraded easily. Low modulus particles can circulate longer as they can squeeze through tissues, avoiding uptake by immune cells. If the particles are highly elastic, they can escape phagocytosis irrespective of their size, or elasticity has no role with respect to phagocytosis. Which of these options do you think is correct regarding elasticity of particles?
Ma'am, 2 low modulus particles can circulate longer.
Okay. Anyone else?
It's option 2.
Okay. Anybody else would like to answer? Okay, option 2 is the correct answer. So low modulus particles circulate longer as they can squeeze through tissues, avoiding uptake by immune cells. In terms of elasticity, the low modulus particles can basically squeeze through fenestrations in spleen like this. So they can easily squeeze through the gap between two endothelial cells. Because of their lower modulus, they can when they are squeezing, it's not affecting their property or they're changing, similar to RBCs. So these lower modulus particles can circulate because they can escape from these immune cell uptake by squeezing through these fenestrations in spleen. And if you're comparing these low modulus particles, if two different sizes of particles, larger and smaller size, are there, even if they are low modulus, larger particles are able to circulate in blood longer as compared to the smaller particles. Okay, moving on to the fifth question. So, pegylation of nanoparticles is a common practice to evade uptake by phagocytic cells. Which one of the conformations of PEG is preferred to maximize this effect? There are different conformations here: brush, mushroom, orientation doesn't matter, triangular, circular, or cubical orientation. Which of these do you think maximize the practice to evade uptake by phagocytic cells?
Option 2.
Mushroom conformation. Okay. Anyone else?
Ma'am, option 2.
Option 2. Okay.
Sorry, I think it's option 1, brush conformation.
Okay. Anyone else would like to answer? Which of these conformations of PEG is preferred to maximize the effect of evading uptake by phagocytic cells? Okay, the correct answer is brush conformation. Okay, so here we have mushroom conformation that basically sits like mushroom in, and there are spaces in between two different peg polymer that forms a mushroom shape. So there is enough space for proteins to get absorbed onto the particles that leads to being recognized by the immune cells. And then we have brush conformation where the polymer chains are such that they form brush like conformation on top of the particles, and they are free to move. So because of their movement, like a brush, they avoid these absorption of proteins onto the particles, which then helps in evading the uptake by immune cells. So this is why the brush conformation is considered better than the mushroom one, and it helps in maximizing the effect of evading uptake by the phagocytic cells. Okay, here's the sixth question. What is the working principle behind enhanced permeation and retention effect? You have to select two correct options here. I'll give you some time to go through the options. Please let me know what you think the correct options are. Working principle behind enhanced permeation and retention effect.
Option 2.
Option 2, okay. And one more. You have to select two options here.
Ma'am, option 5, faulty lymphatic clearance of particles from intratumoral environment.
Okay. And one more.
And option 2.
Okay. Anybody else has any other options other than 2 and 5 or 2 and 5? 2 and 6, 2 and 3. Okay. Anyone else would like to answer? Okay. Option 2 and option 5 would be the correct answer. So, positive pressure between vasculature and intratumoral environment allows flow of particles from vasculature to tumor tissue, and faulty lymphatic clearance of particles from intratumoral environment. So, these are the principle behind the enhanced permeation and retention effect. So, enhanced permeation is basically the positive pressure between the vasculature and the tumor environment that leads to permeation of the particles from circulation into the tumor microenvironment. And then, because of the faulty lymphatic clearance at the tumor tissue, they are not able to clear it properly. Because of that, there is more retention. So, these two would be the correct options: enhanced permeation because of positive pressure and retention because of faulty lymphatic clearance. Okay, here we have the seventh question. Which of the following methods can be used to measure size of nanoparticles? X-ray diffraction, dynamic light scattering, atomic force microscopy, gene transduction, or ballistic gene gun mediated transfer. One and two, okay. Okay. So far we have option 1 and 2. Anybody else has any other option?
Two and three.
2 and 3, okay.
Two and three.
2 and 3, okay. Anyone else? Apart from option 1 and 2 or 2 and 3. Which two methods you can use to measure size of nanoparticles? Anyone else would like to answer? Okay, so the correct answer is option 2 and 3, dynamic light scattering and atomic force microscopy. So, there are qualitative techniques like the microscopic techniques, electron microscopy, or the atomic force microscopy, and quantitative ones, the dynamic light scattering, which gives a more number average, weight average, and volume average parameters, and you can calculate the diameter based on that. So yeah, in XRD actually goes even further, right? It's like the atomic distance it will give, but these ones are more easier ones, the dynamic light scattering and the atomic force microscopy. Okay, next question. Which one of these is not an advantage of nano and microparticles?
Second one.
Okay. Anyone else? Okay. Not an advantage of nano and microparticles. Which one of these is not an advantage of nano and microparticles? Okay, option 2 would be the correct answer here. It can elicit inflammatory reactions in host. So, other than that, all of the options are advantage. This is the only disadvantage because they are still made up of some polymers, and these polymers, whether synthetic or natural, they can elicit some kind of inflammatory reaction in the host. Okay, we have the next question. Which one of the following parameters does not affect microparticle synthesis using double emulsion method?
Ma'am, none of the above.
Okay.
Yes, ma'am, none of the above.
Okay.
Ma'am, option 5.
Option 5. Okay. Anybody else would like to answer? Oh, the last option, that is none of the above, would be the correct answer, because all of these parameters, polymer type, molecular weight, concentration, kind of solvent, ratio of the different solvents, surfactants, steering rate, all of these would affect the particle synthesis. So the correct answer would be none of the above. Okay, here we have a numerical question. I think this was there in your week 3 assignment. The question is, in a membrane reservoir system with 5 micron membrane thickness, 5 mg of drug is released after time t. If the desired release of drug is 1 mg, what should be the thickness of the permeable membrane? You have to give the answer in micrometer. I'll give you some time to solve this and then we'll go through the answer. Okay. So far we have 25 as one answer. Anybody else has any other answer? One. Okay. Anybody else? Let's look at the answer. So here this equation will be used. Mt equals to ATKCS T by L, where T is the time and L is the thickness and M is the drug concentration. Okay, so we have initial membrane thickness 5 micrometer and drug released at time t is equals to 5 mg. So if you want to relate the drug release at time t, and drug release is related to t by L, is directly proportional to t by L. So it's like, or direct, you can directly relate it to thickness. So drug release at T1 by T2 is equals to L2 by L1. So we need thickness of the permeable membrane for to release 1 mg. So if you want to release 1 mg, you need to find out L2, which would be MT1 by MT2 into L1. So initial the drug is 5 mg and thickness is 5, and the desirable concentration is 1, which will give you a concentration answer of 25 micrometer. So the correct answer would be 25 micron. Most of you give the correct answer. Okay, this was the last question I had for today. If anybody else has any other doubt or anything else, let me know, else we can close this session here. Or if you want me to go through any question again, then let me know. Anybody has any other doubt? Seventh question and first question. Okay. Okay, the first question was regarding the proton sponge effect. So the particles, here you have to select two options that is related to proton sponge effect. And as we saw, these two options, the first two options would be the correct answer, where particles carry secondary and tertiary amines, which help in escaping endosomal and lysosomal vesicles inside the cells, and phenomenon which leads to osmotic swelling and bursting of vesicles. So basically inside us, because of endosomes, if your particle enters into the cells, these cell membrane will try to cell membrane or the lysosomal membrane, because of the fusion it is uptaken either by the endosomes. So, and if it fuses again, it will end up with the lysosome as well. So they are basically trapped inside these smaller vesicles, and if they are in lysosome, the pH is already less, so it might degrade the particles already inside the uh, inside this, and it might not be as effective as it was in the cytosol. So for the particle to escape from these endosomal membranes, this proton sponge effect is used, which is basically the particles are made to carry amines, secondary and tertiary amines, that will buffer the pH inside these endosomes. And this is the following things that happens: as the pH of the endosomes get buffered, it requires more influx of the proton from the outside, and then that is followed by the chloride ion transport, and it leads to, because of more ions and transport of these, all of these things, it leads to swelling and bursting of these vesicles, that leads the particles outside of these vesicles into the cytoplasm. I hope uh, you got these answers. And the seventh question was, which of the following methods can be used to measure size of nanoparticles? So dynamic light scattering and atomic force microscopy, these are the two different techniques. So the dynamic light scattering basically the diffusion, it uses a equation uh, where the diffusion constant and based the particles follow Brownian motion, and based on their diffusion constant and viscosity, there is one equation where you can calculate based on their motion, you can calculate the light scattering and then relate it to the size of the particles. And atomic force microscope, in atomic force microscope there is a small probe or a tip that interacts with the particles, and if you have particles layered over a slide or a surface, it can measure the surface. It basically scans the surface, and based on the interaction with the particle of the tip of the atomic force microscope, it gives you information of whatever there is there on the surface. Like it will have some probe like this, and here you have your different particles size. So it basically based on interaction between the probe and the particles, it gives information which you can collect and measure the atomic force microscopy. But I think you are asking mostly about the X-ray diffraction. X-ray diffraction goes even below the nanoparticles. It gives more of an atomic information, and uh, yeah, it gives more of an atomic scale information. You can, if your crystals information basically it gives, but here we are talking about the size of these particles, so basically DLS and atomic force microscopy you can use. uh, I would still think the only the last second and third options are correct. It gives information, but actually I'll have to go
Ma'am,
through this again. Yes.
ma'am, I think XRD can determine the size of nanoparticle, ma'am, by using Scherer equation.
Mm-hmm.
Yes, ma'am.
Okay.
Even I thought that XRD was the right answer. So even I have doubt
Maybe,
in that.
yeah, I see. Maybe some error in the question formation then. I mean, it does give information between the nanometer scale, but yeah, okay. Okay, anybody, any other question anybody wants to discuss? Okay, it's like um, it's not gaining positive charge during endosomal. It is gaining positive charge, but it's not like endosomal transport. Uh, it's uh, your target is not endosomal transport. Your target is basically coming out of this. Somewhat it is right, the phenomena of gaining positive charge, but it's more often the buffering of the endosomal and bursting of the endosomal vesicles and coming out of it. Mm. I mean, if you here, if you see the conjugation of peptides that can create pores in endosomal membrane, these are also kind of proton sponge effect, but it's not necessarily gaining positive charge and doing the endosomal transport, right? So the ones that is basically helping escape it, though positive, gaining positive charge is helping it, but it's not necessarily the positive charge. It's basically the secondary or tertiary amines and the peptides or some other things that is helping in bursting out of the endosomal or lysosomal vesicles. Regardless of the positive charge, they'll enter into the endosomes when they are engulfed by the cell. But to some sense, I think it does make sense because they are gaining positive charge. Yes, you are correct. Any other question? If there are no other doubts, then we'll close the session here. Thank you for joining.